All right, in this video, we are going to talk about the average atomic mass of elements, okay? Now, we've already talked about the mass of atoms, right? We've talked about this concept called the mass number for individual atoms, right? If you wanted to analyze the mass of an individual atom of carbon or oxygen or iron, you would look at what to get that mass? Good. You would look at the number of protons plus the number of neutrons, right? That would give you our mass number. It's not super useful because every time we have a sample that's made up of atoms, we don't just have one atom, right? We have billions, trillions, quadrillions of atoms in our even tiny samples, okay? So it doesn't really become useful to talk about the mass number when we're talking about so many atoms in one sample. Instead, what it's more useful to talk about is the average mass of all atoms within your sample. And that is the average atomic mass, and that is that decimal number that is located on the periodic table at the very bottom of each little box, right? If you had oxygen, it would say 15.999 blah blah blah, right? It's that decimal number that we're talking about now, which represents this average atomic mass. So we have a pretty simple equation for the average atomic mass. I'm just going to call it AAM for short. And it is a weighted average. A weighted average, kind of like how your grades are calculated. You know how homework can be worth 20% of your grades and the tests are worth 40% of your grades. So that tells you the tests are more important to your final grade calculation. Well, the same thing happens with this average atomic mass calculation. We're going to weight this calculation based on how abundant each atom with a particular mass is in the universe, right? So carbon, there are carbon atoms, some have a mass number of 12, some have a mass number of 13, but there are tons of carbon atoms that have a mass of 12 and only very few have a mass of 13. So we weight it so that the number of carbon atoms that have a mass number of 12 kind of takes over the calculation, and it'll end up being closer to that higher abundance. So what we do in order to calculate this weighted average is we are going to take the mass, and I will call this mass with a little 1, and this is just the mass of one of the isotopes of your element in question, and we will multiply that mass, and this is just the mass number, right? Our protons plus neutrons. We're going to take that mass and we're going to multiply it by the percent abundance of that isotope. So I'll call that 1. All right? And then we will add to that the mass of your isotope 2, your second isotope, times the percent abundance of isotope 2. And then you add to that the third one. And then you add to that the fourth one. And you do that until you've accounted for all of the isotopes. Now, sometimes you will only have 2 isotopes. Sometimes you'll have 3, 4, or 5. Okay? You just keep going until you've accounted for all of those isotopes. That will get you the weighted average atomic mass for a given element. All right, let's do one easy example and then we'll do one kind of trickier example. So in this first one, this is just going to be the carbon that I was talking about a little bit. We have our carbon 12 isotope. This would be 6 protons and 6 neutrons in this atom. And this version, or this isotope of carbon, accounts for 98.9% of all carbon atoms in the universe. Okay, so very heavily weighted towards this type of carbon with 6 protons and 6 neutrons. However, there is another isotope of carbon which has a mass of 13. Now, what's changing? What's changing between a mass number of 12 to 13 for carbon? It can't be protons, so hope you didn't say protons. It's only the neutrons, right? So instead of 6 neutrons, it's going to have 7 neutrons, but it's only got a percent abundance of 1.1%, so very tiny amounts of carbon, but not zero amounts of carbon that have a mass of 13. So let's plug it into average atomic mass for carbon into our equation. So what you're going to do is you're going to put this mass, 12, and that's AMU, and we're going to multiply it by its percent abundance. But you don't actually want it in the percent form. You want to actually put it in like the numerical decimal form of the percent. So it's not 98.9%, it's 0.989, right? That's the abundance in decimal form instead of percent. And we'll add to that the mass of our second isotope, which is 13 AMU. Multiply that by the decimal form of the percent abundance, which in this case would be 0.011. And then that's it, right? Only 2 isotopes, so we don't need the plus plus. We stop as soon as we've accounted for all of our isotopes. If you plug these numbers in, solve it on your calculator, we don't actually care about sig figs for these types of calculations because they are all known values. We're not measuring these values to figure them out. They are very known, okay? They've already been studied. They are known with great precision. So we can just plug it in and kind of list what our calculator gives us, okay? So if you plug that in, you'll get something around 12.011 AMU, and if you look on your periodic table, you'll see that number, which means on average, every carbon atom that you find in nature, in the universe, on average, will have that mass, okay? So that's a pretty simple example. Let's do a little trickier one with iron, because iron has more than 2, it's actually got 3 prevalent isotopes, so we'll have iron with a mass number of 54, an iron with a mass number of 56, and iron with a mass number of 57. Now again, what's changing between these 3 isotopes is simply the number of neutrons. Protons has to stay the same because that's what makes iron iron. So 54 has a percent abundance of 5.9%. 56 has 91.8%. And then 57 has 2.3%. Now, you should be able to look just at the percent abundances versus their mass number and tell me when we do this calculation, this average atomic mass calculation, our answer should come out to be very, very close to which one of those masses. Hopefully you said 56 because it's got by far the highest percent abundance. And remember, this is a weighted average. So the higher the percent abundance, the more it's going to contribute to this final answer, this average atomic mass. So that's kind of a good way to check your answer, right? If you get an answer and it's like 6,820, well, that's not anywhere near these mass numbers, so it's obviously wrong. Likewise, if you got a number that's very close to 57 and far from 56, you've also done something wrong because this percent abundance tells you what your answer should be very, very close to. Okay, so we'll plug in all of our numbers. I'm just going to show the first one just for sake of time, but it's 54 AMU times this percent abundance, but in a decimal form, right? So 0.059, and then you'll just keep adding them up. We would have 2 more quantities here plugging in for those second and third isotopes, And if you plug all of that in, you get something like 55.85 AMU. Notice that is very, very close to 56, not so close to 54 or 57, which makes sense because of our percent abundances. All right, that's it.